everyone. My name is Abul Faz. I'm research associate at Manchester University and working on modeling and simulation center. Today I wanted to just present my jobs in terms of developing a code in open source finite element packages code ASRED to calculate it of constraint parameters T, Z, and Q. So probably in the next months, my code will be released. So if you are interested, you can just download the code and just then use it. Let's look at the backgrounds. In two-parameter fracture characterizations, apart from the first parameter, which is K or G, characterize the deformation, crack tip deformations. And the second parameters characterize the crack tip constraints. The first parameter in elastic, which is T stress, is the second distance parameter in the non-singular parameters in the Williams expansions. Q factors quantify the level of stress deviation from a small-scale yielding solution from any type of the crack. These two parameters are important for fracture assessment beside the stress intensity factors and J integrals. I just give you a snapshot of the application of T stress. More or less, I just read some papers and then categorize all the papers about the application of T stress in three different groups. Some of the researchers believes that the T stress can affect crack path stability. Some of the researchers believe that the T stress can affect plastic zoom. And some of the research believe that the magnitude and the direction of crack tips can characterize about fracture toughness. So, but the question is that how we can just compute these parameters. I presented two ways for computation of these two parameters, which I have programming it. The first approach is based on the stress field. If we look at the Williams expansions and look at the stress tensor in the vicinity of crack, we have seen that the non-singularity terms is T stress. T stress can be calculated for any directions that the effect of singularity can be vanished or superposing by additional other stress fields. For example, T stress can be computed for theta, for the direction of theta 0 in front of crack tip by this equation. For this coordinate system, for example, sigma r minus sigma theta is equal to sigma x minus sigma y. Also, we can just compute the T stress in the crack lips by putting theta directions equal to P or minus P by one stress fields. The T stress is plane constraint. For the effect of out-of-plane constraints, we need to calculate the TZ, which is the out-of-plane stress over the combination of in-plane stress. This is one approach for calculation of T stress, a stress field, by two different methods. The third approach, which I programmed, is based on the displacement field. Here, U is the displacement field based on this coordinate system is in x directions. So we can have the effect of displacement over stress intensity factor K1, K2, and T. I just wrote the equation of Williams expansion based on the displacement against. T can be calculated by the displacement field from crack lips, top and bottoms, by the following equations. This is the third method for calculation of T stress. Okay, let's go forward for Q computations. I'm using the following equation, the equation number 1 for calculation of Q parameters. In these equations, we need to have the small scale yielding solutions. For a small scale yielding solution, I model a large disk by radius about 1 meters and displacement boundary conditions controlled by the value of K, which in my case I put it to 250 megapascal over root of n. I've put in the theta directions, it's 0, and then I observed that, for example, the sigma theta can be constant in my small scale resolution between 2 and 5, and the G between 2 and 5. Some information about the mesh. I have using actually a 100 centric mesh with bias of 100,000, which shows that a very coarse mesh far from the center and a very fine mesh near the crack tips. Also, I have using 100 elements for each ring. We should run the models with actually the actual crack material definitions. In my case, I have used the Rambourg-Osgood plasticity model, Rambourg-Osgood plasticity models with material hardening 10, with material hardening equal to 10, and the material coefficient equal to 1. Sy is representative of yield stress of the material, which in my case equal to 400 megapascals. I just give you about my algorithms to calculate it of these two parameters. The user only can define the crack tips. So I calculated the location of the crack tip and all stress and strain field in all relative nodes. If there is any node, we can catch up this node. If there is not any node, I projected the stress on the specific direction, or our preferred directions. Then stress can be interpolate and extrapolate from a specific distance, because this distance is very important. This distance r is important. For larger value of r, the higher terms of Williams expansion can be noticeable. When the r is equal, for example, equal to 0, we have the effect of singularity. So for this issue, I just get the distance. I just calculated the first element that attached the crack tip as a distance. So the user can actually calculate it, how many elements needed. For example, how many distance needed, 1 element, 2 element, or so. For computation of Q, first the small scale yielding solution will run with the same material definitions, and then the Q factor can be computed based on the theta equal to 0 direction and the r equal to between 2 and 5. I validate my programs with two simple standard test cases. The first one, single edge notch specimen, and the second one, elliptical cracks. You can find the material definition of each of them for saving of time. I don't read it, but let's look at the result. For the first single edge notch elements, the result is around 2% different from analytical solutions. I haven't get exact equal because TS is computed based on 3 different methods, so the user can just actually select one until now actually. So it's around something like that, which is around 2% with analytical solutions. Second approach in 3D body, the actual result is around 5% different with analytical solutions. Okay, let's go to the second part. I just implemented my constraint function for a welded pipes. These pipes are combinations of 2 stainless steel joints by aggrieve welds and also repair welds. The repair weld present here as a pink colors. The weld length is 6 meters with 80 centimeters diameters and 35 millimeters as a thickness. I have implemented a crack in this pipe at the center of the repair welds. If I just back, the repair weld is not in the center of the pipe, so we have actually a distance around 3 millimeters above the center. This true thickness crack started from inner surface to outer surface and cover around 48 angles. Cover all these surfaces. We putting the pipe in the 4-point bending. We putting the pipe in the 4-bending experiment. In this slide, you can see the experimental procedure. We attach 2 arms in here and here to representing of the 4-point bendings You can see the distance and also the supporting point and the loading points. For modeling a strategy, I'm modeling a half of the pipe using symmetry, and also for supporting point, due to the representing exactly the experimentals, I create a rigid ring parts. In terms of boundary conditions, for the limitation for moving a pipe in the axial directions, I just fixing of the center of the pipe in x directions. Supporting point should be limited for any rotation and displacement. Boundary should be implemented based on, actually load should be implemented based on the displacement in y directions, and the rest of rotation and displacement should be put into 0. This is just overview of my meshing. Normal, actually I have used it around 146,000 8-node linear break elements with 52 numbers in the radial directions and 80 numbers element in circumferential direction just for the crack regions. For the rest I have using a very coarse actually mesh. Since this material is not well treated, so there is a visual stress inside of the weld, I have the experimental of visual stress in two different paths, repair path here and opposite repair path in the other side. For implementation of the visual stress, I have creating two zones, map zone 1 and map zone 2. Since I implemented the visual stress as an initial stress in the model, so my model is not actually converged. So I needed to do using a converging equation to be actually converging in terms of static converging. So I implemented the visual stress without any crack first. Our prefer is to have the major visual stress is equal to resultant visual stress. But we need to have an iterations. After actually, first the input of visual stress should be equal to measures, and then the result can be calculated. This result should be as an input of the next generation of the iterations. After 16 iterations, my model are converged, and you can see that the result with the axials and the Hooper visual stress for two different zones. The difference between visual stress in this area is around, let's say, 5% difference. Actually, it's a good match in terms of a good match. Since we don't have any analytical solution for this, I have imported my mesh to the abacus and computed my strategy with abacus. The black linear lines shows the abacus result, which is actually completely linear, and also three different strategies which I have developed. Abacus using as integration integrals for calculation, for computation of T stress. So, for each crack tips, all we take an integrals, and any, let's say, an accuracy of the stress in one point cannot affect it in the final results. But in the downside, inaccuracy can be set from one crack tip to another ones. You see here that the calculation of the stress based on the two stress field, sigma xx minus sigma yy, presented a better result because the singularity effect of one field of stress can be vanished by the second ones. Then I have implemented the visual stress, and then only using of my strategy for computation of T stress. By implementation of T stress, the results are increasing by around 15%. Then I have calculated TZ and Q parameter for our pipes. T stress for extreme point should be 0, and there is not any changing by implementation of visual stress. Also, we have the same scenario for Q factors. Let's go to the conclusions. Three different approach programs are robust, since inaccuracy of a stress intensity factor cannot affect it on the results. Between three strategy, actually using of the stress in two different directions can give it a better, let's not say a better let's say, better results. Because in singularity of one field in one direction can be vanished by the other directions. After introduction of the residual stress, we have actually increasing of the stress, we're increasing the TSS around 15%. This is a part of ongoing research, and I haven't finished it about the pipe actually yet. So this is only for just validation of my quotes. And that's it. Thank you very much, and I'm happy to answer any questions that you have.